So our last skill in this learning unit on thermodynamics allows us to connect concepts of free energy, delta G, with something we've spent 3 learning units thinking about, which is equilibrium. And so one of the important things that's part of what we're going to discuss here is how we can change spontaneity in a process that has temperature dependence by changing the temperature. So if we think about this, remember our example from before, something that has a temperature dependence means that entropy is either helping or hurting us. And at some point, as we change the temperature, we'll get to a point where we transition from delta G being negative to positive or positive to negative, depending on whether temperature is helping or hurting. But the idea is we go through kind of this 0 point. We go from delta G being large and negative and spontaneous to all of a sudden becoming small and negative, and then becomes small and positive, and then large and positive. And so we transition through a 0 point. That 0 point we call the pivot point. Okay, so again, knowing that if delta G is negative, it's spontaneous. If delta G is positive, it's non-spontaneous. We must go through some point where delta G is transitioning between spontaneous and non-spontaneous, and that's when delta G is equal to 0. So if we take this equation and we set delta G equal to 0, we get delta H equals T delta S, and by solving for T, we get this equation. So we can solve for the pivot point by taking delta H and dividing by delta S. So one of the things that we'll have to make sure is this tells us what the pivot point is, but we need to know, based on whether entropy is helping or hurting, whether we'd want to be above or below this pivot point in order to have our process be spontaneous. So let's look at an example here. Let's take this copper oxide reaction here. This is a non-spontaneous reaction, meaning it does not occur without the additional input of energy. And it doesn't occur at low temperature, but it does at high temperature. Okay, so we're going to do some predictions here, right? So if it doesn't occur at low temperature, but does at high temperature, all right, that should mean that entropy is something that's helping our situation, right? Because we want to be adding to that. So we could say here that we know that entropy is going to be positive, but you know what? Looking at this equation, we probably should be able to predict that. Looking at this, we've got 2 solids on the left and a solid and the gas on the right. We are going to be having more favorable entropy when we make more molecules move more and when we have more gas molecules. So we're moving in a direction to make more gas molecules. So we are increasing in our entropy with this process. So entropy is positive. Well, since this is a reaction that we already said has a temperature dependence, that must mean that enthalpy is not helping us. So if enthalpy is not helping us, we know that enthalpy must also be positive. It must be an endothermic reaction. So if that's the case, we know, and here we can see this, the lower the temperature is, right, the more unfavorable this process is. But as we get to higher temperatures, we allow this part of this term to become dominating, and it's going to be able to compensate for our unfavorable positive enthalpy, and will allow us to then switch to delta G being positive. So to find where this pivot point is, they call it a crossover temperature here, we can set this equal to 0 and then solve for T. So that's how you're going to do problems like that. Another concept that's kind of important in this section here, we've mentioned it already before, is this idea of reaction coupling. So this has to do with thinking like Hess's law. Remember, we could add up chemical equations that have their associated enthalpies, and we can get an overall enthalpy for a combined process. And the same is true here. So when we have a reaction, and bringing in and tying in some earlier units, if we have a reaction that is spontaneous, but it's just a slow process, we can use a catalyst to speed up our reaction. And we'll tie this in a little bit here when we revisit kinetics. But what if you have a non-spontaneous reaction? Is there a way that you could help a non-spontaneous reaction? Catalysts aren't going to help that, okay? But we can do something called reaction coupling. So let's take a look at this copper oxide reaction here, a different copper oxide reaction here. But this has a very unfavorable delta G. But notice this, we've got a situation where the product of our first reaction is a reactant for our second. So we can couple these together. We've seen this already with looking at problems with enthalpy. So by coupling these two together, so this again is a common piece that we find in both of these, we can add these and sum these up together to get our overall process that is spontaneous because it has a negative delta G. Coupling is a concept that is essential for thinking about how many biochemical processes work that are largely unfavorable from this energy standpoint. All right, one other important equation from this learning unit is this guy here. Delta G equals minus RT times the natural log of the equilibrium constant. Again, equation that will be provided for you, but it is an equation. I want you to know how and when to use it, but it basically allows us to connect the spontaneity of a reaction with the equilibrium constant. All right, so remember our number line, right? If we've got something that favors products, it's going to have a large equilibrium constant. Putting a large number in here is going to end up giving a large negative delta G. So reactions that are spontaneous have large negative delta G values and large equilibrium constants. And the flip is also true. If we have a very small equilibrium constant, we're going to lie on the reactant side, and we're going to have a delta G that's going to be positive. Okay, it's going to be non-spontaneous, and that kind of makes sense. We're non-spontaneous. We don't make product. We're living on the reactant side. So tying this all together with some concepts that we've already learned about with thinking about equilibria and shifting equilibria, we talked about Q versus K comparisons with equilibria. And any time that you are at some place that is not where you want to be, remembering that Q represents where you're at, K represents where you want to be, anytime you are not at where you want to be, it is going to be a spontaneous process to get you there. Think about K kind of being this spot, this low point, if you will, on your energy minimum, on your energy landscape where you want to be. And if you're uphill anywhere on that, you're going to want to get to that downhill spot. So one of the things to keep in mind, notice here, if we're product heavy, we talked about this in our equilibrium chapter, right? We're going to have our equilibrium shift to make more reactants. And this is a critical concept to kind of make sure we understand. If we are going to shift to be able to make more reactants, we are not going to have that same forward reaction happening. We can't have the forward reaction keep happening. That's going to keep making more products. We need to turn around and do the other reaction. And we flip reactions all the time. And remember what happens to our thermodynamic parameters? We take the negative of that, right? Negative delta H, and now we'll see negative delta G. So you can do that with flipping reactions, okay? If Q and K are very different from one another, then you've got a big downhill slide to get from where you're at to where you want to be. If they're nearly the same, we're not going to have a lot of free energy that's released because you don't have very far to slide from where you're at to where you want to be. So those concepts of Q and K come into play here, but because there's this connection between K and delta G, we can actually see the magnitude of how much energy is going to be given off. Okay? So highlighting, if we are not at where we want to be, if Q does not equal K, delta G will always be negative. But you may have to switch the direction of the reaction. So if we've gone past kind of the point where we want to be, the only way to go backwards is to switch the kind of chemistry that your reaction is doing. We need to flip that reaction. So make sure conceptually that you understand that. All right, so how do we solve these equilibrium problems? You might have a problem that asks, which way will this reaction shift? And that really boils down to a Q versus K comparison. So if you are given a delta G value, okay, you can use this equation to tell you what K is, right? So you can get the equilibrium constant for a process. And then using the values that are given for where you're at, you can solve for Q, and you just do Q versus K. If Q is less than K, then your reaction needs to continue on towards product. If Q is greater than K, you actually have to turn your reaction around, do the reversed reaction to remake some of your reactants. So stuff that we already talked about in equilibrium, but now we can say if we are given a delta G value, we can still do these kinds of problems. All right, big picture to kind of think about here is revisiting reaction coordinates. Because reaction coordinates, even though we drew them before with delta H, it's really better to think about them in terms of free energy, because the spontaneity of a process really is more than just the enthalpy contribution. Entropy is an important part too, and delta G really allows us to think about both of those. So we still need to be able to think about how to draw a reaction coordinate here. So you've got two axes here. We're going to have reaction progress on our x-axis, and we're going to have free energy on our y-axis. You'll notice I didn't write delta G on that, right? Because when I'm taking the difference in the free energy values for two species, that's how I'm going to get delta G. So for example here, if we've got our reactants at a certain energy level, and let's assume that we've got a spontaneous process, so we go downhill in energy between our reactants and products, the difference between these two energy values is going to be our delta G. Okay, let's finish drawing our reaction coordinate here, and then we'll label some more parts. Remember, a reaction coordinate always goes through a peak and then kind of comes down here. This energy difference between reactants and the height of that peak is our activation energy, and in this case it's going to be the activation energy for the forward process. You'll notice that we have two activation energies that we could draw here. This is the activation energy for the reverse process. And just to map on here, because we talked about how we make things faster, if I make a lower hill here, that for example happens when we have a catalyst or a special biological catalyst, which is going to be an enzyme, we can lower that energy, and so we will lower our activation energy. So this is the activation energy for a catalyzed process. Okay, so let's map some of these pieces on here, this language that we have here, because reaction coordinates are really important to allow us to visualize what we call the energy landscape for a chemical process. We're going to address, again, questions with our reaction coordinate of how fast. So when we think about how fast, that really is the height or the size of our activation energy. So this tells us how fast our process is. Noticing that when we have a catalyst or an enzyme that we've added, we've decreased the activation energy, so we've made that reaction faster. So that's what enzymes or catalysts do, is they take a reaction and they make it faster. So let's map on a little bit about what this delta G value tells us. So there's two parts that we're going to get from delta G. We're going to either get that it's positive or negative, and in this case, we're going to have our delta G being negative. Remember, delta is always final minus initial, products minus reactants. Our product energy is lower than our reactant energy, and so we've got a smaller number minus a larger number. That's how we get that to be negative. And the sign of this tells us whether. It tells us the spontaneity. So this is the whether piece. Whether this is spontaneous or not. Remembering that a negative delta G is a spontaneous process. So as we've drawn this here, this is a spontaneous process. There's another part that comes from our delta G, and there's going to be the magnitude of it. That is the value, the numerical value of what delta G is. The larger the delta G is, the more product we're going to be making. So we can relate this to how much. Remembering that we can relate delta G and our equilibrium constant. Delta G equals minus RT times the natural log of our equilibrium constant. In this case, the larger the delta G value is, the larger the magnitude of this is, the larger our equilibrium constant is. Remember, equilibrium constants are products over reactants. So large equilibrium constants mean large concentrations of products. So when we talk about how much product we make, we can get that from the magnitude of delta G. All right, so last little piece here that's also going to allow us to tie into some concepts we're going to learn in our next learning unit on electrochemistry, and that's thinking about non-standard conditions. I haven't really said too much about this, but all of the values that we see on Appendix B and so forth have this little, it looks like a degree symbol, but it actually stands for what we call naught. So we'll say delta G naught or delta S naught. This naught means we are at standard conditions, which is 0 degrees C, 1 molar concentration, and 1 atmosphere pressure. We actually saw standard conditions when we did gas chemistry back in Unit 5 in Gen Chem 1. So these standard conditions are important because they allow experimentalists to directly compare data that they collect under these same conditions. But not all science operates at these standard conditions, and this is especially important in biological sciences because our body temperature isn't 0 degrees. We generally don't have 1 molar concentrations of biological molecules in our body. Now, we do tend to live at atmospheric pressure, so this tends to be okay, but we're very non-standard with the rest of these. All right, so what does that mean? Well, if we want to think about what the delta G is at these new conditions, we need to consider where we're at. So what we're going to do is take delta G naught, and then we're going to add RT ln of Q. And Q just really represents where you're at. So how is where you're at different from where you might want to be? So we're going to see this work again in our electrochemistry chapter when we understand how batteries work and how we can use this to explain that. All right, so how would you solve kind of a problem that has to do with these non-standard conditions? You'll need to use this equation, and basically you're going to calculate delta G naught using Appendix B or the other ways that we've talked about that you could calculate delta G naught, and then you will use the non-standard conditions that are provided to calculate Q and then correspondingly the RT ln of Q piece to this. Now, sometimes you might have non-standard conditions that boost or augment your delta G, and sometimes you might have things that diminish it. It depends on where you are at compared to where you want to be. And you'll see that kind of played out mathematically as you do these calculations. So that's pretty much it for our learning unit here on thermodynamics.